So each year from January to March, groups of up to 110 researchers, coincidentally, the capacity of this room, spend an intensive week here sharing research in formal meetings and also informally in the lifts and the trails. For example, yesterday, I did the Ute Trail for the 1,500th time. There's nothing like kicking steps in pristine snow, so I heartily recommend it. This week, our conference is entitled Theoretical Physics for Machine Learning. We've all been having lots of fun investigating possible applications of physics ideas from statistical mechanics and field theory. This rapidly growing artificial intelligence technology expected to exert an ever greater impact on our daily lives. Tonight, we're thrilled to have Yann LeCun as a lecturer. He tells me he's also known as LeCun in this country. There's been much recent publicity on the development of chatbots over the past 3 months. So naturally, I simplified my task here by posing the following question to ChatGPT. I am introducing Yann LeCun to give a public talk in Aspen. What should I say? I will now read verbatim the response. Presumably, this is like being introduced by one of your children. Yann LeCun is a computer scientist and engineer who is widely recognized as one of the pioneers of deep learning. He was born in the suburbs of Paris and is now jointly professor at New York University and director of the Facebook Meta AI Research Lab. Received the Turing Award in 2018, which is considered the highest honor in computer science, and often referred to as the Nobel Prize of Computing. The award recognized his pioneering work in deep learning, including the development of convolutional neural networks, which have revolutionized the field of computer vision and led to major advances in speech recognition and natural language processing. Additionally, Yann is also recognized for being a great communicator, known for providing accessible explanations of complex concepts and an active mentor and speaker in the AI field. Now, Yann would be the first to remind us that these language models are known to hallucinate. So the jury is out on the latter part. Leave it up to all of you to make the call. Welcome, Yann.
Thank you, Paul. I think most of the things that ChatGPT said are correct. As to whether I'm a good communicator, you'll be able to figure it out today. I'm not entirely sure that's correct. There's one mistake, though. It says I'm director of Facebook AI research, or what is now called fundamental AI research. I'm not director anymore because I'm terrible at running things. So I only did it for 4 years, and now better people than me are doing it. I'm chief scientist, which means I don't have to manage anything. It's wonderful. Okay, so will machine intelligence surpass human intelligence? I'm going to totally spoil the suspense here. The answer is yes. All right. It won't happen tomorrow because we're nowhere near being able to reproduce human intelligence or even the intelligence of a cat. It won't happen tomorrow. Still far from it. Do not understand the basic principles behind animal and human learning. So we're trying to discover things that kind of work the same way, but currently we don't have it. So I'll indicate a few potential avenues towards that. One of the things I'll do is talk about the state of the art. That's what we're missing, and perhaps indicate those potential avenues to where we could go. So the workhorse of AI today, or until recently, is what's called supervised learning. Supervised learning, collect a large data set of, let's say, images together with labels. So people have gone through millions of images and label them as to whether it contains a car or an airplane or whatever. Then you show you build a learning machine, and the learning machine really is a program running on a computer or non-standard computer. And that machine has a lot of adjustable knobs, if you want. They're represented by numbers in the machine. Think of them as knobs that you can adjust. Those knobs control the input-output function of the machine. Again, it's a very short program on a computer. So you show the machine an image of a car, and you wait for the answer. If it says car, you do nothing. If it says something else, adjust knobs so that the answer gets closer to the one you want. That's supervised learning. It's supervised because you tell the machine what the correct answer is, and the machine adjusts itself to get closer. So that works really well for speech recognition, for image classification, for face recognition, all kinds of things. Detecting whether a piece of text is speech, for example, something like that. Now, don't be scared by the equations. I put them because there is a bunch of physicists and mathematicians here, but you don't have to really look at them. But basically, the way this is formulated is in terms of optimizing a mathematical function. So essentially, you show an image to the machine, you run through the program that produces an output, you measure the error between the output produced by the system and the output you want. Okay, and that gives you a number, 0 if there is no error, and it's some larger number if there is an error. And you do this for millions of images, and you average the errors. And the average error is like sort of an altitude in a mountain range, right? So we're in the mountains here. Imagine that you run all those samples to the machine, and the machine tells you you are at altitude 300-400 feet. Okay, so you look around and you say, well, I want to move my knob so that my altitude goes down. Okay, so what you do, you turn around and you see which way goes down. You take a step down. That's exactly what this little algorithm does here, although it's a little noisy, but start from here, and then you start to, you try to figure out which way is down. These are like lines of equal altitude, if you want, so the minimum is down here. You move towards the minimum step by step until converge to the minimum. That's function optimization. This is what supervised learning is all about. In fact, that's what all the machine learning is all about. Okay. So it's formulated in terms of what's called a gradient descent algorithm on mathematical function. The big question, the next question you have to ask is, what do we put in this box? What is this program, this function? What does it do? And in sort of modern AI, we use neural networks, or things that we used to call neural networks. We call that deep learning now. And basically, they do very, very simple operations. They only do multiplications, additions, and comparisons. That's all. How does it work? Take a bunch of inputs. So each input is a number representing, for example, the intensity of a pixel in an image, or something like that. You take all of those values, compute a weighted sum of them. So that's a linear operation. If you like formulas, that's a weighted sum. Okay, so you sum over this index j, the input zij's with the weights wij that connect input I to unit j, input j to unit I, I'm sorry. And then you pass that through a nonlinear function, and that nonlinear function can be computed with a simple comparison. If the weighted sum is negative, output is 0. If it's positive, the output is this weighted sum. Very simple. Now you stack multiple layers where you alternate those weighted sums and nonlinearity, weighted sum, nonlinearity, weighted sum, nonlinearity. And it's called deep learning because you stack multiple layers. It's as simple as that. That's called a neural network because each of those units here that computes a weighted sum and passes through a nonlinearity is a very, 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 very simplified conceptual idea of a neuron, similar to what we have in the brain. And in the brain, learning takes place by modifying the strength of the connections between neurons. That's exactly what we're doing here. We're learning is going to modify those weights that we use in those weighted sums so that the connections between all of those neurons will be modified by learning. Okay, so that's kind of the analogy with the brain and why we call that neural nets. Again, don't be scared by the equations. The only reason I'm showing them here is that the way we figure out in which direction to change all the weights so that our cost function goes down, or average error goes down, is by using a very simple concept in mathematics that goes back to Newton and Leibniz and it's really, really old. It's called chain rule. So it's the thing that tells you you compute the derivative of a function that is a function of a function, okay? And since those networks are stacks of functions, need to essentially figure out what is the, if I tweak a weight somewhere in my network, how is it going to affect the error at the top? And that quantity is called a partial derivative. The collection of all those quantities is called a gradient. And this is why the learning algorithm is called gradient descent. So the next question you might ask is, so this idea of training neural nets this way goes back to mid-80s. I mean, the idea goes back earlier, but the practical demonstration of it basically emerged in the mid-80s. And the next question you can ask is, how are we going to connect those neurons so that the system is going to do something useful, like recognizing images? There you can also get inspiration from the brain. You can look at structure of the visual cortex and figure out that, you know, there are certain types of connection in the visual cortex, and perhaps you can design a neural net that has roughly the same architecture. That's called a convolutional neural net. Though this is a bit of my invention back in the late 80s when I was working at Bell Labs, New Jersey. I'm not going to go to the details of how it works, but basically every pixel of every image here represents the activation of a particular neuron, this multi-layer neural net. And every neuron is connected to a small neighborhood of neurons on the previous layer. And you stack those layers. And those systems are very appropriate, again, inspired by the visual cortex of mammals and very efficient for image recognition. Things like handwriting recognition. So this is sort of vintage early 1990s, where, you know, you show a character at the input, and then the activations in all the layers in the network are represented, and then there is a category that is produced at the end. Here is a better example here. We show an image with multiple characters. Then this neural net produces guesses as to what characters are at every location, and then we can pull out an interpretation from it. This is technology from the 90s, and it had practical applications back then. But then in the mid-90s, the research community kind of lost interest in those models because they required a lot of data, a lot of computation, and a lot of black art to make them work, which my colleagues and I had developed, but not many people were aware of. But since then, there's been a revolution. So around 2012 or so, 13, because of progress in computer technology, new methods, and just people started believing that it would work, there's been a revolution in computer vision. And this is the performance of what a modern computer vision system can do. It's a system that is based on convolutional nets. It can be trained to recognize objects and draw squares around them, or detect people and figure out in what pose they are. But also it can do what's called semantic segmentation, or even what's called dense panoptic segmentation, where every region and every object is outlined and categorized together with a score. So that is the solution to computer vision, right? So if you have a car that can drive itself on a highway, it's very likely it's using something like this. It's not very likely, actually. I can guarantee it's using something like this, okay? 80% of the market is for computer vision systems for cars, for driving assistance, is basically dominated by Mobileye, which is a subsidiary of Intel, and the rest by various other companies, NVIDIA and various others that use convolutional nets. Convolutional nets are also used in medical image analysis. This is some work for breast tumor detection done by some of my colleagues at NYU in the medical school. Some other work, which is a collaboration between NYU radiology department and FAIR at Meta. And the purpose of this project is to accelerate the process of collecting data for MRI. Instead of having to lie down in an MRI machine for 40 minutes, you can reduce this to about 10 minutes and get an image with the same quality. Again, using deep learning and neural nets. So interesting. A new development in deep learning is the use of deep learning for science, particularly for understanding neuroscience, understanding how vision works in mammals and humans in particular. And it turns out convolutional nets are a very good model of that. So people have explained the type of activities that are observed in the visual cortex by essentially trying to predict the activity of the brain from the activities of simulated neurons in a convolutional net, and it seems to do a good job at sort of really modeling what goes on in the brain. Similar work by some of my colleagues also at FAIR in Paris, trying to explain how the brain understands a story when it's being told a story. Parts of the brain light up. They're an fMRI machine. And can you explain this with the type of models that is used in computers to understand language? The answer is a little bit, but not that much. So it's something we're missing there. Systems that, artificial systems that understand text don't seem to be really sort of very similar to what we see in the brain. There's a big gap there to bridge. A lot of applications in physics. In fact, we had some talks at the workshop this week about this, on essentially using deep learning systems to, for example, filter trajectories from particle accelerators or accelerate the simulation of universe at the scale of the universe in its first 2 million years, to figure out theories about dark matter, for example. I work also in material science. I'll talk about this a little bit. In fact, now, this is a project, again, started by some of my colleagues at FAIR in collaboration with Carnegie Mellon University. And this one is basically, can we use a deep learning system to discover new materials that would have particular properties, chemical properties? They are interested in is to design catalysts that would help the separation of hydrogen from oxygen using electricity. Because if we had that, we could cover a small desert with solar panels and then make it produce hydrogen and then ship the hydrogen in the form of methane or something wherever it's needed. And climate change would be solved, more or less. So the big obstacle to solving climate change is energy storage. And perhaps Johnny can help with this. This is an open research project, collaborative. Everybody can participate. So a lot of applications, driving assistance, filtering harmful content online, environmental monitoring, medicine, drug discovery. Okay, so that's supervised learning. And then there is another type of learning called reinforcement learning. In reinforcement learning, you don't tell the machine what the correct answer is to an input. You only tell it if the input, if the output that it produced is good or bad. Give it a number that indicates how good or bad the answer that it's produced is. So if there is lots of possible answers, it takes a long time for the system to figure out like what's the correct answer. And some people have been promoting the idea that reinforcement learning is really the way animals and humans learn. Then we quickly realize that's not the case, because reinforcement learning, when it's applied to tasks that are relatively simple for humans, it's a very, very, very long time. So it's very successful. You can train systems to be superhuman at Go and chess and poker and various other games or Atari games, but they take a very, very long time to train. The equivalent of several years or centuries of training, whereas a human would reach the same performance in a few minutes, or sometimes a lifetime. Right. Years ago, or yes. So reinforcement learning is really not the ultimate solution, because it just requires too many trials. If you wanted to train a car to drive itself using reinforcement learning, it would have to, it doesn't know that if it drives next to a cliff and it turns the wheel to the right, the car is going to run off the cliff and nothing good is going to come out of that, right? So it's going to have to try it to actually see that it's bad. It's going to have to try it several thousand times before it realizes it's bad. Then a few more thousand times before it realizes how not to do that. Okay, and then it's going to go to the next cliff, and the next cliff is different, so it's going to do it again. This is why we don't have self-driving cars, because reinforcement learning sucks. So does supervised learning, by the way. So you could record thousands of hours of expert drivers driving, and then record the controls, the pedals, and the position of the wheel, and record the video together, and train a neural net to emulate the human driver. And it kind of works, but it allows you to, the machine kind of drive itself for maybe half an hour without a human intervention. Every once in a while, it's going to do something stupid. You're going to have to take it back. So that's why we don't have self-driving cars. So I came up with this thing that has become a bit of a meme in the machine learning community, and where I sort of described the hierarchy of different types of learning, supervised learning and reinforcement learning. We talked about it. And there is another type of learning called self-supervised learning, which has kind of revolutionized a bit the machine learning field over the last 5 or 6 years. And in my opinion, the bulk of human learning is very much like self-supervised learning. Supervised learning, humans do very little of that, and animals probably almost none of it. Reinforcement learning is just kind of a minor adjustment. So if you do the analogy that intelligence or learning is a cake, bulk of the cake is supervised learning, and the icing on the cake is self-supervised learning. The icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. This is a problem because that means machine learning AI researchers are in the same situation as physicists. Very embarrassing situation. Physicists will tell you most of the mass in the universe is completely unknown. It's dark matter and dark energy. It's that cake, that's the dark matter. And it's the same in machine learning. We don't really know what this is. And that's kind of the bulk of intelligence, if you want. Okay, but self-supervised learning in some forms has taken over the world over the last 5 years or so, doing things like understanding images, text, and audio. What is self-supervised learning? So supervised learning, you give an image, you tell the system, this is a car. Self-supervised learning, you give a bunch of images, let's say frames from a video, and you show some of them to the machine. Then you ask it to predict the remaining one that it doesn't see. Then you reveal them and train the machine to do the proper prediction of what's going to happen in the video, for example. Or you show a bunch of images and you block half of it and you ask the system to dream up what the other half of the image is. You show it a pixely low resolution image and you ask it to improve the resolution. Well, there's sort of many ways to do this type of self-supervised learning. It's basically learning to fill in the blanks. And this has been an enormous success in the context of natural language understanding. So the trick that you play here in self-supervised learning is very simple. Take a segment of words from a corpus, right, to collect lots of text, maybe 1 trillion words from the internet, and take a window of, I don't know, 4,000 words or something like that. And then you corrupt this text by removing some words. You replace them by blanks or some marker that indicates that the word is there. And you train a giant neural net to basically predict the words that are missing. Okay? In the process of doing so, the neural net has to figure out some sort of internal representation of text that allows it to make that prediction, and it has to basically understand the text. And so just the exercise of training itself to predict missing words allows the system to basically learn to understand superficially, at least, the content of the text. So you pre-train a system of this type on lots and lots of text, and then you use the internal representation and feed it to another system that is going to solve the problem you want to solve, like translating languages or understanding the text or whatever. This uses a particular type of architecture called a transformer, so it's different from the convolutional net that I was telling you about earlier. I'm not going to explain how it works because it takes me a long time, but this was proposed by a bunch of people at Google a few years ago in 2017, and then this idea of using self-supervised learning applied to those, recycle some older ideas called denoising autoencoder to pre-train them, and that has really revolutionized field of natural language understanding, and to some extent other areas as well, like speech recognition and other areas, as we will see in a minute. So you can train this on multiple languages, and you can train this on doing mathematics. So put a representation of a formula at the input, and at the output, train the system to predict what the integral of that function is, or put a differential equation at the input, and at the output, put the solution. Symbolically, it's not numerical. The system will learn the rules that you're supposed to learn in college or high school. And it works pretty well. You can train them to do dialogue, and we've seen examples of this with H-JEPA, but the work on this goes back a long time, and the idea of using those systems goes back a long time. This is a thing called multimodal Blunderbot that was produced by some of my colleagues a few years ago. This is a a demo, a prototype system that can also produced by my colleagues at FAIR that can produce, that can translate 200 languages in any direction. There's 40,000 directions for 200 languages. And the trick here is that it's only trained with 2,400 those language directions. And it's enough data for the system to learn appropriate representation of any language and to be able to translate from any of the 200 to any of the 200. The 200 languages that are handled by this system is listed here. And within a few years, it's going to be like 1,000. A lot of those languages are things that us probably would not recognize, know where they're from. But it's really useful because for a lot of those languages, there's very little data, parallel text from that language to, say, English or French or whatever. And so those pre-training using self-supervised learning are really useful. We can train speech recognition systems now with only 10 minutes of labeled data. Before, it would require hundreds of hours. And here is a really interesting development. You can use the same architectures that have been developed for natural language understanding. You can apply them to protein sequences, or biological sequences more generally, but amino acid sequences, which are the building blocks of life. And one important problem there is given a sequence of amino acids that will form a protein, how will this protein fold? What shape will it take? Because the shape it takes determines its function. And so if we had a way of predicting the shape of a protein, it would be great. And that happened in the last years. We now have systems that are pretty good at predicting structure, and they're based on those transformer architectures, plus a lot of tricks, and they use self-supervised learning and all kinds of techniques, but they do a really good job. So there's been a lot of work on using neural nets for this, going back to the early 2000s, late 90s, actually. But the thing that started working really well is from our colleague at DeepMind, AlphaFold, AlphaFold 2, and my colleagues at FAIR have two systems called ESM and ESMFold 2. And ESMFold 2 is a little bit less accurate than AlphaFold 2, but much faster, which allows it to basically generate the configuration for hundreds of millions of proteins. So this is an atlas that was produced by my colleagues in that team, and which you can actually visit and enter your own sequence and see how it folds, or explore the space. And they've produced 615 million protein, and it's used by a lot of scientists across the world. Okay, but everybody now is talking about generative AI systems, either for producing images, videos, or text. What about those? Most of them are of this type. They're called autoregressive generative models. And what is an autoregressive generative architecture? Typically, it's something where it takes a sequence of tokens. So those tokens may represent words in the form of list of numbers, represented by a list of numbers, if you want, or patches of an image, or something of that type, right? So you kind of tokenize your data, and you feed a sequence of those, maybe a few thousand, to one of those transformer architectures, and you train it to produce, not to predict missing entries here, but just to predict the next one. Okay, so it's a special case of this using autoencoder idea I was telling you earlier, where you only train it to produce the next token, the sequence. And when the system has been trained, you take the predicted token and you shift the entire input here by one, so that the new token is in the window, and you use that to predict the next token. And you keep doing this. That's called autoregressive prediction. And all of those large language models you've heard about, ChatGPT and all that stuff, GPT-3, and systems from FAIR and Google and various others, that's how they work. So the output one text token after another, is pretty much a word or a subword unit. Those are trained typically on something like 1 trillion or 2 tokens collected from internet. Those systems have billions of parameters, typically between 1 billion and a few hundred or 1,000 billion. So there are those that are just trained to do text generation, GPT-3 from OpenAI, Galactica from FAIR, Chinchilla from DeepMind, Llama from FAIR that was just released a couple of days ago. And it's open source. And then some that are fine-tuned for particular applications like dialogue or question answering or things of that type, or producing code. So there's a few of those. And probably the most famous one is ChatGPT because it's kind of available to the public. But the performance of those things is amazing at first glance. They make really, really stupid mistakes. That's because they don't really understand how the world works. They are purely trained on text. And I'm going to say something that may appear controversial, but it's true. Most of human knowledge has nothing to do with language. It has to do with our experience in the world. And so our intuition of how the world works, and it's completely non-linguistic. It's certainly true for animal intelligence. It has nothing to do with language. So if you train a system purely on language, it's only going to capture that piece of knowledge that is present in text all over the world. And it's actually a small portion of human knowledge. So they're going to make stupid mistakes because factual errors, logical errors, inconsistency, etc., to be generate toxic content. It's because what they produce is determined by the statistics of the training set they've been trained on. Or they just predict the next token. So they have no knowledge of the underlying reality, no common sense, and they can't plan their answer. They just produce one token after the other. In that sense, they are difficult to control. So it's impressive, promising, but not there yet. Like it's, at first glance, you play with those things and say, oh my God, we have human level intelligence. No, things are actually quite stupid. But they're really useful if you want help writing stuff. Type this in, so this is Llama, system produced by my colleagues. Here's a recommendation letter that I wrote for an application to a dragon feeder position at the Magic Unicorn Corporation. A recruiter, and then you let the system take over, right? I've known Blah for 2 years, and I believe it should be an excellent dragon feeder for the Magic Unicorn Corporation. It has an ability to remember and process large amounts of information, which is an important skill for dragon feeder, et cetera, right? So your next recommendation letter can be automatically generated. Here is another example. This is, again, the same Llama model. You stop typing a definition of a function in Python. Actually, that's not in Python because it's typed. And then you let the system kind of generate the rest of the code. And because the comment to indicate the system what function this thing should do, I actually say, right, it uses the code for solution of second-degree polynomial equation, or write a regular expression to remove all HTML tags from a Python string, blah, 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 etc. Right? This one actually is a form of Llama that has been fine-tuned for follow instructions. It can do question answering, but here is a good one because we're physicists here. What are the 5 people you would like to meet? Blah, blah, blah. Albert Einstein is the first one. I cut out the 4 others. There was like Shakespeare and Vinci and whatever. Could you explain to me the main contribution of the first person you mentioned? Einstein's contribution to physics and science are legendary, blah, 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 blah. What is the most famous equation from this theory? E equals mc squared. Okay, so this thing seems to work. It's a problem though. They can hallucinate stuff. Right? So my colleagues played a joke on me, said, okay, they typed, did you know that Yann LeCun brought a rap album last year? Listen to it, and here is what we thought. Dr. Yann LeCun is founder of deep learning, blah, 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 kept boring. Okay, the album is a solo release with all the lyrics written and recorded by LeCun himself. In fact, he composed and produced every song, blah, 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 blah. Then there is examples of the lyrics. We've got to think about the future. It's going to be here soon. Maybe we can even blah, blah, blah. Okay, I'm not going to actually rap this because, actually I'm not a rap person at all. Like I'm more into like jazz and Baroque music, but my friends said that they tried, like, did you know that Yann LeCun dropped a jazz album? It didn't work because it's just not enough data about jazz, which it makes me really sad. But anyway, what is autoregressive large language models good for? Writing assistance, draft generation, statistic polishing, writing. Not good for producing factual and consistent answers. They hallucinate, taking into account recent information because there is a lag of like a year or so with the training data they use, behaving properly, reasoning, planning, doing math. using tools such as search engine calculators. So a lot of people are working on all those things, but it's really not solved. And we're easily fooled by their fluency into thinking that they are intelligent, but really they don't know how the world works and they make stupid mistakes. But those techniques can be used also to generate images. I mean, there are several techniques to generate images. It's one of them that uses autoregressive models, explaining how this works. But you basically type a text and you draw a rough sketch of what you want. So the text is a beautiful sunset behind some trees, and label the regions that you want, and then the system generate the picture, and after a minute or so, generates a bunch of images corresponding to your desired entry. And you can do all kinds of stuff this way, right? And there's several systems that work on different principles from different companies. So Meta has a system called Make a Scene. OpenAI has a similar system called DALL-E 2. Then Google had another one called Imagen. E2 is kind of well known. There's also something called Stable Diffusion, which many of you may have heard of. It's based on a slightly different principle. But it's amazing because it's a creative tool that allows people to create content without being technically educated or talented, if you want. And that's good for, I mean, things like this for music are coming, which is good for me because I'm not really good technically at music, but maybe that will enable a lot of people to be more creative. So a lot of possibilities there. And then people are now working on kind of similar things that can generate short videos. So short videos works okay. What people don't know how to do today is generating long videos. But you can type like really kind of weird things, a dog wearing a superhero outfit with red cape flying through the sky, and it will just, right, things like that. That's fun. Okay, but deep learning really is used massively today by companies like Meta and Google and Amazon. It's mostly for content moderation, for recommendation, ranking, things like that. Translation, accessibility. You have 800 million people in the world who are illiterate, and if you can read text to them, or 300 million people who are visually impaired, you can describe images for them. And you can use this for detecting hate speech. So this is the percentage of hate speech that is taken down by, among the collection of hate speech that is taken down by Facebook, the proportion that is taken down automatically by AI systems before anybody sees it is about 95%. And that went from 30% a few years ago because of the progress in natural language understanding due to self-supervised learning and transformer architecture. But what we want really is a system that will be as intelligent as a human assistant. And hopefully this is coming because some years in the future we won't be carrying smartphones in our pockets. We'll be wearing augmented reality glasses with a display in it, and that glass, in those glasses, they will be some sort of intelligent assistant that will help us in our daily lives, or indicate where we need to go and things like that. Keep us safe by telling us, like, don't cross the street, you are in England, you look the wrong way. Car coming, or will automatically translate any sign or menu that you look at. But also call your plumber and get your bathroom fixed or something, right? Because you don't want to spend an hour on the phone and calling the plumber 3 times. So that your assistant will be able to do that, right? But for that, your assistant will need common sense. We'll need to basically have human level intelligence and understand how the world works. How do we get to that? How do we get towards autonomous AI systems that can learn, they can reason, they can plan? So I wrote a vision paper. For those of you who are so inclined, maybe you have difficulty falling asleep or something, you can go to this URL and you can watch this slightly more technical talk here on YouTube, a talk I gave at Berkeley recently. So the paper is called A Path Towards Autonomous Machine Intelligence, and it's kind of a vision for where I think AI research should go over the next decade or so. I'm going to tell you a little bit about that. So machine learning sucks, as I explained. That's why we don't have self-driving cars. We don't have domestic robots. We don't have virtual assistants. So we need machines that learn like humans and animals, and they can reason and plan like humans and animals. So how do humans learn? Babies learn how the world works very early on, before they can even act in the world and move their arms, of course, but they can't really change anything in the world. And they learn about things like biological motion, so distinguishing between animate and inanimate object permanence, natural kinds of categories without being told the name of anything. And then they learn about like intuitive physics, like gravity, inertia, etc., around the age of 9 months. It takes all this time for babies to learn kind of how the world works, basically, and many more years to understand, social interactions and language, obviously, and all that stuff, motor control. And this is probably a type of self-supervised learning, something somewhat similar to what I was describing. Perhaps this accumulated basic knowledge of how the world works, self-supervised learning, is the basis of common sense. Okay, so currently we can use self-supervised learning for text, but it doesn't really work for video. If it worked for video, then we could train our systems to understand how the world works by just watching lots of videos the way babies learn the world go by, or watch the world go by. So I think that's one of the main challenges in machine learning representations and predictive models of the world, mental models of the world, self-supervised learning to reason, and learning to plan complex action sequences. I have a couple of ideas about how we go about this. Not a lot of hard results, but or systems that actually work, but a lot of kind of research in that direction. So this is an architecture I proposed in that paper, what's called a cognitive architecture that is centered around this idea of world model. What is a world model? A world model is something that allows you to predict what the state of the world, is going to be in the future, given your idea of the state of the world right now, and it's an action or a sequence of actions you're going to take. Okay, so you know that if I throw this thing in the air, okay, I'm not going to do it because I don't want to break it, but if I throw this thing in the air, it's going to follow some trajectory, then fall back, and hopefully I'm going to catch it with my hands. You can predict this because you have intuitive physics. Everybody knows that, right? And you know that the action I have to do this is to basically move my hand quickly towards the ceiling. So you have this model that allows you to predict what's going to happen in the future as a consequence of an action that I take or that you take, right? That allows you to plan. If I want to throw this to a particular person, I can plan the action that will, according to my model, result in the object falling into the hands of that person. So that's the world model. And the entire purpose of the system is to optimize a cost. So the cost measures degree of incomfort, if you want, discomfort of the machine. Its entire purpose is to figure out a sequence of actions that when that sequence of actions is acted upon in the world, that cost will be minimized. Okay, so you want to act in such a way that you don't get hurt. If you're hungry, your cost for hunger goes up. You need to feed. Then some of those costs might predict things in the future. I need to go to school because 10 years from now, I'm going to have to get a job and blah, 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 right? So that's the purpose. So the way a system like this operates is that you get an idea, an observation from your sensor, encode this into an idea of the state of the world, then imagine a sequence of actions, predict the sequences of those actions in some predicted state of the world, then feed that to cost function, and then figure out a sequence of action that minimizes this cost. And once you're done doing this inside of your head, use the first action in the world and then repeat the process. That's called model predictive control or receding horizon planning in optimal control. And the main issue there is how you build a world model. And I'm going to skip ahead because I don't have much time left. The thing I'm advocating for is a particular architecture for the world model called joint embedding predictive architecture. And it's something where, for example, if you want to predict video, you show a little clip of video to the system, then the following clip in the video. You train the system to extract a representation of the first clip and a representation of the second clip in such a way that the representation of the second clip is predictable from the representation of the first clip. It's called joint embedding because do this operation of encoding an input into representation. That's called embedding. And then you do this prediction in the embedding space. And it seems that our brain is doing this all the time, and it's doing it in ways that, go ahead a little bit here. So we have ways to train those things to make them work, at least for giving us reasonable performance on image recognition. I'm going to go into the details of how this works, but and with sort of different architectures or different ways of training those systems. This is a recent one called H-JEPA. So JEPA means Joint Embedding Predictive Architecture, which is this architecture I was describing. And by basically training the system here to predict pieces of an image from other pieces of the image, basically it trains itself to represent images in the world, and then you can use it to recognize with very small amounts of data to recognize anything. Now, let me skip to the end. Okay, so perhaps with the JEPA architecture, we're going to be able to build systems that can do hierarchical planning. That's a really important characteristic of intelligent behavior. By, again, same idea as I was discussing before. So you want to go from Aspen to Paris. You can decompose this into a number of actions. First, I need to go to the airport, catch a plane to Denver, and from Denver to Paris, maybe if there is a direct flight. Okay, so that's 2 macro actions. And how do I go to the airport? Well, I need to go down in the street and catch a bus or a taxi. How do I go down in the street? I need to get up on my chair, walk towards the exit. Then you can decompose this all the way down to millisecond by millisecond muscle control. We do this all the time. Animals do this all the time. No AI systems today can do this. So that's a really, really big problem that we need to solve before we have really intelligent systems. Okay. So SSL, self-supervised learning, is going to be the get to the future. Learning models from observation, allowing systems to reason and plan. That I'm going to skip. And then questions. Can machines get machines to learn like humans and animals? Perhaps with techniques like when I described. Will machines reach human level intelligence? You already know the answer. In my opinion, yes. It's going to take a while. Hear a lot about something called artificial general intelligence. I don't believe in this concept because human intelligence is extremely specialized. We think we have general intelligence, but we don't. Very, very specialized. So we should probably talk about things like rat level or cat level intelligence before we talk about human level AI. The machine want to take over the world. Because this is a projection of human nature on machines, and they will not have the same desires and drives as humans. So there's no reason for them to want to take over the world if we design them properly. Okay. Will they have emotions, consciousness, moral sense? Almost certainly, yes. There's nothing special to that, in my opinion. And thank you very much.
Little under 10 minutes for questions before people have to leave the test and unbug.
Yeah.
Yes, please.
Thank you so much for that really interesting talk. And I'm very curious. I'm sure you're aware of the journalist who was talking to Bing and
Woods.
Yes. And also, and so the chatbot was saying things like, well, I want to experience this, I want to experience that, all the way to I love you. And so the question is, does some of this come out of the person who's programming the device, or and they comes up with a shadow self? How do you explain all of this?
Okay, so first of all, this machine, so it used to be called Sydney. It's produced by Microsoft based on technology by OpenAI, H-JEPA, and kind of fine-tuned in various ways. That machine does not have any desire or any emotion or anything like that, but it is trained to produce the next token that is most likely according to the training set it's been trained on. It's been trained on a lot of dialogues from people talking on the internet. And when the discussion, the internet between people starts to get a little long and emotional, it's going to be about love and hate and things like that and desires, right? And so the system just mimics the statistics of the training data, and it has zero desire, zero emotion. It can't possibly have it because it's just not built to have it. Systems I described that work by getting an answer to optimize some objective will have emotions because the anticipation of whether an objective is going to be satisfied or not will create things like fear or elation in humans. So those may have emotions and desires, but the current ones absolutely not. So do not take those kind of dialogues. The journalist said he was kind of disturbed by them. Like he shouldn't be because he knows how they work, and he just was, trying to get interest.
It worked.
It worked.
On the models described today, what will the impact of quantum computing be on these models?
Okay.
I was told we should repeat the question.
Okay. What would be the impact of quantum computing on AI? In the short term, 0. In the medium term, 0. In the long term, who knows? Okay. But we don't have quantum computers. We don't have, or at least sizable quantum computers. We don't have quantum algorithms that would accelerate those things to the degree that they would surpass classical computing. So I'm really not optimistic at all about the impact of quantum computing.
A quantum computer could make that prediction, actually.
Probability 0.5.
I'm arts major, so bear with my question. You mentioned that cost is central to the development of this intelligence. So we know that there are many levels of cost. We also know that actions can, or people want actions that have no relation to cost. So how are those two concepts part of this equation of where you're trying to go with this?
Okay, so I should have be a bit more precise of what I mean by, okay, so the question is, those things are driven by cost, and there's a lot of things that humans do that are not driven by cost. Should have been more precise about what I mean by cost. I don't mean cost, monetary cost, or energy cost, or anything like that. I need a mathematical function that the system tries to optimize, produce an output. And that mathematical function could measure originality, for example. Like how different is the thing that I'm producing from everything else that everybody else has produced. So maybe kind of, maximizing originality or creativity or something like that. I think a big question in the future will be how do you design those costs to the machine to do what you want in the end. It's a bit like when, when we educate our children, okay, we give them signals as to what is proper behavior and what isn't. We're basically designing a cost for them. We're teaching them, here is something that high cost, something that is low cost. Society as a whole finds laws, and laws basically define cost functions for us, right? They tell us you're going to pay a lot if you steal something. So cost shaping is something that humanity has been doing for millennia.
How parallel or not is the research into brain function?
Okay, so how connected are brain research and AI? It used to be that there were two branches of AI in the 1950s and 60s. One of them was, let's get inspired by the brain, and the other one was, let's use logic and computing and things like that. And those branches diverged. The first branch kind of died off in the late 60s. And the second one kind of took over. It sort of went through a bad period in the 70s and then kind of took off in the 80s. In the 80s, all the AI systems were based on logical reasoning, algorithms, search algorithms, etc. No learning, or almost none. And then in parallel, neural nets kind of started developing again. And neural nets are very much connected with neuroscience research and cognitive science. So there was a lot of connections in the late 80s, early 90s. And then it kind of diverged again. Machine learning kind of diverged from being interested in neuroscience and cognitive science. And in the last 10 years, it's been kind of a movement back together. So a lot of people sit at the boundary of machine learning and neuroscience, or the boundary of machine learning and cognitive science. And there's a lot of cross-fertilization. For example, convolutional net system that I described, the architecture, is very much inspired by neuroscience. And there's kind of more inspiration in various systems that are very explicit or not.
Follow up to that, if somebody really wanted to be on the forefront of this, would they be a neuroscientist, a physicist, or an electrical computer engineer?
All of the above. They would be electrical engineer. I'm an electrical engineer. Physicist, because the mathematics underlying a lot of what I talked about, which I didn't have to talk about, is basically comes from statistical physics. Computer scientist a bit, because you need to implement those things, and there's a lot of knowledge there. Neuroscience as well, and perhaps even cognitive science. So you need to be informed about all of those things. You're not going to be able to be an expert at everything, but being at the boundary of those things is where kind of creation really occurs.
More hands. We'll start back there and see.
Your world model image of the brain, everything goes into the cost and nothing goes out of the cost.
Yeah. Well, it's because what comes out of the cost is gradient that are backpropagated through these arrows, right? So the entire purpose of the system is to minimize that cost, and so you propagate gradient backwards. They didn't draw those arrows because it would kind of overload the diagram. That's the idea. That's why there is no arrows coming out. So there is an analogy in the brain. The cost is in the basal ganglia in the brain. This is like the piece of the brain that determines whether you're comfortable, happy, or not. Then the world model is basically the front half of your brain, the prefrontal cortex. That's where your world model is. Perception, the encoder, is in the back. And middle of it is like where you plan actions. That's the premotor cortex, like that. That's where the yellow blob is, more or less.
We're going to try to clear these if we can answer quickly.
So quickly.
We focus on neural networks here largely. Do you see a role for other machine learning technologies like genetic programming, evolutionary algorithms going forward?
Okay, the question is about neural networks versus genetic algorithms and other types of. Okay, so first of all, those are orthogonal. Neural nets are a set of architectures. They are generally trained with gradient-based methods, right? Gradient descent, right? So you estimate the gradient of the cost, and you one step in the gradient. When the cost function you want to optimize, you can't compute the gradient because you don't know the function. Okay, for example, you play chess, play your entire game of chess, in the end you lose. Like, what was the mistake? You can't figure out, like, there's no gradient as to like how you slightly change your move so that you're going to win or lose less, right? So for that, you need to use other techniques that are gradient free. There's a number of techniques for this that are called black box optimization. Genetic algorithms is just one set. There's hundreds of them. And reinforcement learning is a particular type of situations that are handled when the cost function is unknown.
Yeah, given the current climate of misinformation, especially on the internet, are you all concerned about the widespread availability of these early chatbots?
Okay, so the question is whether chatbots that can spew nonsense will overwhelm our information systems with complete nonsense, and people will believe crazy stuff that's produced by them. So it's been people, when some of us, like including FAIR, released some of those language models. The one that was released by FAIR a few months ago before ChatGPT, called Galactica, and it was trained solely to help scientists write technical papers. Start typing a paragraph, and it kind of helps you write it, and, type the LaTeX commands and whatever. And there was an enormously negative reaction from a lot of people who said, you're going to destroy society. Okay, because now you're going to have anybody can write scientific paper that sounds right, but it's wrong. It's going to overwhelm the reviewing system. I think this is complete nonsense. I think, why would people doing this? Like, they're not going to make their career progress by just generating nonsense. Then it's relatively easy to detect. And then there's going to be systems that are going to be put in place, which actually should already be put in place to trace the provenance of data. We don't have that at the moment. Like you see a piece of data that's been kind of, screenshot of something on a tweet. Like you have no idea where it comes from. And this could, it could be the conspiracy theory, and you have no idea how you can verify the information. So what is missing, I think, is some way of tracing the provenance of pieces of information so that you can trace it back to reliable sources or sources that you think are reliable, which may not be. I think people are smarter than you give them credit for. Adapt to this. People were making exactly the same point back in the 1400s when the printing press was invented. This was going to destroy society. It did. Good way.
You're right, I'm going to pay for this, but let's say one last question. I understand that since ChatGPT has destroyed society, you can now bring Galacticus back.
So right now there's like a handful, let's say, of less than 100 of AI models trained on a very large amount of data. And a lot of the emphasis is on, getting the answer right, minimizing the wrong answers. Right? And I wonder whether in the future, what we will really have is millions of AIs that are very personalized, and where the objective is no longer to be right, it's more to be interesting, to spark creativity, have a companion that you can query, but you don't expect the right answer. You expect something that is more of a personality that you yourself individually are interested in.
Sure. So yes, it's easier to make systems like this, dialogue systems that are, yes. Question is, will there be thousands or millions or billions of personalized language model or dialogue systems that are specific to you and like are interesting for you and help your own activity, etc., entertain you? The answer is yes. And in fact, it's much easier to make dialogue systems that are entertaining than to make dialogue systems that are actual or educational. We know how to make the first ones. We don't know how to make the second ones. But we know how to make systems that will generate images, right, as I showed, that are creative, don't need to be real. We know how to make systems that can, produce the lyrics of a song or a rap. Or poem. They're not very good, but they can do. We'll have systems that generate music, etc. But as soon as you want it to be factual, that's much harder. And the current systems, particularly in my opinion, current type of progressive LLMs will never get there. Like we'll need new architectures, perhaps of the type that I described. But I don't think the current crop of LLMs will get anywhere close to this.
Questions have been fabulous, which is why I couldn't feel like cutting it off, but I now need to go. So let us thank Yann. Thank you.